The universe is a masterpiece in progress, carved by forces you cannot see. These cosmic sculptors shape everything, from the delicate swirl of a galaxy to the largest structures in existence. By the end of this journey, you will understand the invisible hands that mold reality itself. How did a formless cosmos become so beautifully structured? And what mysterious substance provides the hidden framework for it all? What does it mean that we are part of this ongoing creation? This cosmic canvas is not a rigid stage but a dynamic, breathing entity. Think of spacetime as a vast, elastic fabric, a canvas that can stretch, bend, and ripple. It is the essential medium for every cosmic event, from the orbit of a moon to the collision of galaxies. The revolutionary insight from Einstein was that mass and energy do not simply sit within this space, they actively mold it. A star, a planet, any object with mass creates a depression in this fabric, much like a bowling ball would stretch a taut trampoline. This curvature is what we experience as gravity. It is not a mysterious force pulling at a distance, but the simple, elegant geometry of an object rolling along a contoured surface. A planet orbits its star not because it is being pulled, but because it is following the invisible groove carved into the very fabric of reality. This warping is the sculptor's first and most crucial tool, the initial chisel stroke that dictates the motion of everything we see in the heavens. Without this pliable, responsive canvas, the universe would be a formless, silent void. The stage itself is an active participant, setting the rules for the grand performance, and the primary artist working upon this canvas is the relentless force of gravity. Gravity is that master sculptor, the lead artist in a cosmic studio whose silent work never ceases. It is the force that called out to the sparse, primordial mist left by the Big Bang, coaxing wisps of hydrogen and helium to gather, to condense, and to ignite into the very first stars. Sir Isaac Newton gave us the mathematics to describe its pull, a force of attraction between all things with mass. But it was Einstein who revealed its true nature, showing us that this pull is not a mysterious string between objects, but the experience of moving along the curves and contours of spacetime itself. This curvature operates over distances so vast they defy human comprehension, pulling not just stars together, but entire families of galaxies into clusters, and those clusters into immense superclusters, the largest known structures in the cosmos. It is gravity that gives a star or a planet its spherical shape, as every part of the object pulls toward a common center, smoothing it into a perfect orb over eons. It dictates the elegant orbital patterns of solar systems and drives the majestic, swirling rotation of entire galaxies. Without its relentless, unifying pull, the universe would remain exactly that, a formless, ever-expanding and silent mist of isolated particles. This invisible force provides the bedrock upon which all large-scale reality is constructed, and the first and most magnificent demonstration of its power is the galaxy. That first master sculptor, gravity, faced an almost empty canvas. For millions of years after the universe began, it was a dark, featureless sea of gas. Then a subtle shift occurred. A region of this cosmic gas, just slightly denser than its surroundings, began to exert a stronger gravitational pull. It started to draw in more material from the void, growing heavier and denser with every passing eon. This was the seed of a galaxy, a single point of imbalance that gravity would amplify over hundreds of millions of years. As this colossal cloud of hydrogen and helium collapsed in upon itself, it did not simply fall into a single point. Instead, it began to spin, a slow, cosmic whirlpool set in motion by the gentle, uneven tugs of gravity from all directions. This rotation prevented a total collapse, instead flattening the cloud into a vast, spinning disk, much like a ball of pizza dough stretches and flattens as it is spun. Within this immense, swirling disk, gravity continued its work. It pulled together pockets of gas, compressing them until they grew hot enough to ignite, sparking the first brilliant fires. These were the first stars lighting up the darkness, and with each new star, the galaxy grew brighter and more defined. The specific shape that emerged, whether a perfect spiral like a cosmic pinwheel, a smooth, featureless ellipse, or a chaotic, irregular mass, was a direct result of that initial collapse. The speed of the spin, the amount of available material, all of these initial conditions were locked in by gravity and played out over unimaginable timescales. Our own home, the Milky Way, with its graceful, star-filled arms spiraling out from a brilliant core, is one such masterpiece. Its structure is not an accident. It is the signature of gravity, a slow, deliberate signature written across billions of years. Yet for all its power, gravity alone could not have created the universe we see today. There is a profound mystery here. When we observe how quickly galaxies spin, we find a problem. The visible stars and gas are moving so fast that the gravity from all that we can see should not be strong enough to hold the galaxy together. These spinning islands of stars should have flown apart long ago. They did not. Something invisible, something that exerts a tremendous gravitational pull but emits no light, must be holding them together. This is the first great clue to our missing ingredient, a hidden framework within the cosmos. That missing ingredient is the universe's hidden framework, a cosmic scaffold we call dark matter. Think of it like building a magnificent cathedral. You see the grand arches and the stained glass, but holding it all up is a skeleton of steel and stone that remains out of sight. Dark matter is that unseen support for every galaxy in the sky. We cannot see it, touch it, or detect it with any telescope because it does not interact with light at all. It does not glow, it does not cast shadows, and it does not block our view. Its presence is revealed only through its immense gravitational pull. When astronomers measured how fast stars orbit the centers of their galaxies, they found something astonishing. The outer stars were moving so quickly that the combined gravity of all the stars, gas, and dust in the galaxy should not have been nearly strong enough to hold them in place. According to the laws of physics, those distant stars should have been flung off into the emptiness of intergalactic space, yet they remain securely bound to their galactic homes. The only explanation is that there is far more matter present than what we can see. This matter forms an enormous, diffuse halo that envelops each galaxy, a giant sphere of invisible particles that provides the extra gravitational glue. This dark matter does not just hold existing galaxies together, it acted as the essential blueprint from the very beginning. In the primordial universe, slight ripples in dark matter provided the gravitational seeds that attracted ordinary gas, guiding it to collapse into the first stars and galaxies. It is the cosmic skeleton that dictates the large-scale architecture of everything we see. Solving the mystery of what dark matter actually is remains one of the greatest quests in all of science. And this invisible framework sets the stage for structures of a scale so vast they challenge our very perception of reality. This cosmic scaffold of dark matter does not create isolated islands. It weaves an entire universe. Zoom out far enough, and the scattered galaxies resolve into a pattern of breathtaking grandeur, a delicate cosmic web. This is the ultimate masterpiece of dark matter's invisible hand. Picture the largest structure imaginable, a network of ghostly filaments stretching across the void for billions of light years. These are not made of stars or glowing gas, but of the unseen dark matter itself, drawn into long, river-like strands over countless eons by its own relentless gravity. Where these invisible threads cross and knot together, their combined gravitational pull becomes immense. It is at these dense intersections that we find the most magnificent structures in the cosmos, immense clusters containing thousands of galaxies, all held in the grip of dark matter's hidden architecture. The galaxies we can see are merely the visible tracers, the glittering ornaments hanging upon this vast, unseeable framework. They form along the strands and at the nodes like dewdrops condensing on a spider's silk, revealing a pattern that would otherwise remain completely hidden from our eyes. How can we be so sure this web is real if we cannot see it directly? Supercomputer simulations that model the entire evolution of the universe provide a stunning answer. When scientists program the laws of physics and the known ingredients, including dark matter, and press play, they watch as a formless primordial soup evolves over billions of simulated years. The result is always the same, an intricate web-like structure emerging naturally, a perfect match for the large-scale galaxy maps we observe through our telescopes. This cosmic web is the final, conclusive evidence that an invisible framework truly exists, shaping everything on the grandest of scales. But to see where this magnificent design first began, we must journey back to the very birth of time itself. But to find the origin of that cosmic web, we must listen to the universe's very first sound. In the first fleeting moments after the Big Bang, the cosmos was not silent. It was a searing, opaque ocean of primordial plasma, a roiling chaos of particles and energy, and within that intense heat, sound waves propagated through the infant universe. These were not sounds as we know them, traveling through air, but massive pressure waves surging through the dense, hot fluid of the early cosmos. Where these waves compressed matter, they created regions of slightly higher density. Where they rarefied, they left behind areas that were a little more empty. You can think of these oscillations as the very first ripples on a universal pond, the initial, faint impressions that would become the blueprint for everything to come. As the universe expanded and cooled at a ferocious rate, these acoustic waves were suddenly frozen in place, their patterns imprinted onto the fabric of spacetime itself. These tiny variations, these minute hills and valleys in the density of matter, became the gravitational seeds for all future structure. Every galaxy cluster, every filament of the cosmic web, and every vast, empty void can trace its lineage back to the specific pattern of these primordial sound waves. We are not theorizing about this, we have seen it. The evidence is etched across the entire sky in the form of the cosmic microwave background radiation, the faint, cold afterglow of the Big Bang. This radiation is a snapshot of the universe when it was just 380,000 years old, a baby picture of cosmic structure. The specific hot and cold spots we detect in this ancient light are the direct imprint of those density ripples, the frozen sound waves from the dawn of time. By reading this pattern, scientists can discern the exact conditions of the infant universe, its composition, and its geometry. These tiny fluctuations were the starting gun for the cosmic sculpting process, providing the slight irregularities that gravity could then spend billions of years amplifying into the majestic structures we see today. Yet, this entire process of creation hinges on a single, violent event, the rapid expansion of space itself that gave these ripples the room to grow. Yet, just as gravity was building its grand cosmic web, a far more mysterious force was preparing to take command of the entire universe. This is dark energy, the most enigmatic sculptor of all. While gravity works patiently to pull matter together, dark energy acts as a repulsive force, causing the very fabric of space to stretch and the universe's expansion to accelerate. Picture an artist who, while carefully carving a statue, also constantly stretches the canvas, pushing all the pieces of the sculpture farther and farther apart. This bizarre phenomenon was not a theoretical prediction, but a shocking discovery made in the late 1990s. Two independent teams of astronomers were studying distant stellar explosions, supernova, to measure how fast the universe was expanding. They expected to find that the expansion was slowing down over time, pulled back by the collective gravity of all the matter in the cosmos. Instead, their data revealed the opposite. The universe's expansion is not slowing, it is speeding up. It is as if you tossed a ball into the air and watched it not only fail to fall back down, but fly away from you faster and faster, defying all expectation. This discovery of an accelerating cosmos pointed to the existence of a previously unknown energy permeating the vacuum of space itself. The leading idea is that dark energy is an intrinsic property of empty space, a constant energy density that causes a repulsive gravitational effect. As the universe expands and more space comes into existence, more of this repulsive energy appears, driving the expansion to accelerate even further. This sets up a cosmic tug of war on the grandest possible stage. On local scales within galaxies and clusters, gravity is the dominant force, successfully pulling matter together to build the structures we see. But on the vast intergalactic scales, where the fabric of space itself becomes the dominant player, dark energy wins. It works to push galaxies and clusters apart, diluting the cosmic web over immense spans of time. This fundamental competition between the sculptor that builds and the force that disperses will ultimately determine the final architecture and the ultimate fate of the entire cosmos. The discovery of dark energy completely reshaped our understanding of cosmic destiny, revealing that the universe is not only expanding, but is being driven apart by a mysterious, invisible pressure. What does this mean for the ultimate fate of the grand designs being carved by gravity and dark matter? At the densest knots of this cosmic web, we find cities of light. These are the galaxy clusters, the largest structures in the universe bound together purely by the force of gravity. A single cluster can contain hundreds, even thousands of individual galaxies, all orbiting a common center of gravity in a slow, majestic dance that spans millions of light years. This is the ultimate expression of gravity's power to gather and build. Within this celestial metropolis, a clear hierarchy emerges. At the very heart of the cluster, you will often find a true giant, a colossal elliptical galaxy. These monsters have grown to immense sizes over billions of years through a process astronomers call galactic cannibalism. Their powerful gravity relentlessly pulls in smaller neighbor galaxies, tearing them apart and absorbing their stars, growing ever larger and more dominant. The space between these galaxies is not empty. It is filled with a superheated, thin gas known as the intracluster medium. This plasma is so incredibly hot, it glows not in visible light but in powerful X-rays. In fact, the total mass of this invisible, searing hot gas is greater than the combined mass of all the stars in every single galaxy within the cluster. It is a hidden ocean of matter, another reminder of how much of the cosmos exists in forms we cannot see with our eyes. These mighty clusters are not the end of the story. They themselves are gathered into even larger associations known as superclusters. Our own Milky Way resides within the local group, which is part of the sprawling Laniakea supercluster, a vast collection of over 100,000 galaxies. But there is a crucial difference. While a galaxy cluster is tightly bound by gravity, a supercluster is not. These immense structures are so large that they are not held together. Instead, they are being stretched and pulled apart by the accelerating expansion of the universe driven by dark energy. They represent the temporary pinnacle of gravity's sculpting power, the largest patterns it could weave before the stretching of space itself began to dominate. Within these clusters, gravity's work is far from finished. It is in these crowded environments that the most dramatic and violent acts of cosmic sculpting take place. Deep within the heart of that brilliant galactic core, a silent giant resides. At the center of nearly every large galaxy, including our own Milky Way, there exists a supermassive black hole. These are not the vacuum cleaners of popular imagination, but something far more profound. They are gravitational singularities with masses equivalent to millions or even billions of suns, all crushed into a point of infinite density. Their presence is felt not through destruction, but through a subtle, pervasive influence that shapes their entire cosmic neighborhood. Think of them less as monsters and more as the powerful, unseen engines at the very center of a galactic metropolis. Their immense gravity dictates the frenetic orbits of stars in the inner core, whipping them around in a high-speed dance that reveals the engine's incredible mass. But their true power is revealed when they awaken, when a supermassive black hole actively feeds on the gas and dust swirling around it. It transforms into the most luminous object in the universe, a quasar or an active galactic nucleus. The infalling matter doesn't just vanish, it is compressed and heated to incredible temperatures in a glowing accretion disk before crossing the event horizon. This process releases a torrent of intense radiation and can launch jets of energized particles traveling at nearly the speed of light, stretching for thousands of light years into intergalactic space. These jets are not merely spectacular light shows, they are potent sculpting tools. They carry colossal energy out into the wider galaxy, heating the vast reservoirs of cold gas that are the raw material for new stars. By superheating this gas, the black hole prevents it from cooling and collapsing to form new suns. This is a cosmic feedback loop of breathtaking scale. The galaxy feeds its central black hole, and the black hole, in turn, regulates the galaxy's growth, preventing it from becoming too large too quickly. It is a balancing act between creation and suppression. On an even grander scale, those powerful jets can carve out immense cavities in the superheated gas that surrounds entire galaxy clusters, pushing aside matter and influencing the ecosystem for thousands of galaxies. The supermassive black hole is not just a resident of the galactic core, it is a fundamental architect, its violent activity woven into the very recipe for a stable galaxy. These jets are more than just cosmic fireworks, they are titanic sculpting tools. When a supermassive black hole unleashes a jet, it is a geyser of raw power, a focused beam of particles and radiation traveling at almost the speed of light. This jet does not simply fade into the blackness. It slams into the thin, superheated gas that fills the space between galaxies in a cluster. The collision is violent and immense. The jet pushes this gas aside, excavating a pair of gigantic cavities on either side of the galaxy, each one large enough to swallow thousands of solar systems. These are not empty voids, but bubbles of intense magnetic fields and energetic particles, rising like cosmic balloons for hundreds of thousands of light years. They reshape the entire environment, pushing and compressing the surrounding gas, and in doing so, they can trigger or halt the birth of new stars across the cluster. A similar, though smaller, process occurs throughout the galaxy itself. Not all sculpting comes from the central black hole. The lives and deaths of the most massive stars contribute their own powerful forces. These brilliant, short-lived giants do not shine quietly. They radiate so much energy that they literally blow their own outer layers away in a constant, searing stream called a stellar wind. And when their lives end in colossal supernova explosions, they blast the remains of their forged elements out into the galaxy at tremendous speeds. The combined effect of countless stellar winds and supernova can generate a galactic-scale wind, a river of hot gas and newly created heavy elements like carbon, oxygen, and iron that flows out of the galaxy entirely. This grand exodus is a crucial form of feedback. It is the universe's way of self-regulating its growth. By ejecting this gas, the galaxy effectively shuts off its own fuel supply for future star formation, preventing it from burning through all its material too quickly. But this is not a loss, it is a redistribution. The gas and the precious heavy elements forged in stellar cores are sprayed out into the intergalactic medium, seeding the vast voids with the raw ingredients for future planets and ultimately for life. These energetic outflows from both the central black hole and the galaxy's stars act as the final chisels and fine grit sandpaper. They refine the rough structures carved by gravity and dark matter, adding detail and regulating the cosmic cycle of birth and death. This constant exchange of matter and energy connects the fate of a single star to the evolution of the entire cosmos. Every star is a temporary vessel of cosmic potential. It begins its life within the cold, dark nurseries of nebulae, vast clouds of gas and dust left over from earlier stellar generations. Here, a local pocket of the cloud, nudged by a passing shockwave from a distant supernova or simply succumbing to its own weight, begins to collapse. Gravity pulls more and more material inward, the core heats up, and when the temperature and pressure reach a critical threshold, nuclear fusion ignites. This is the moment a star is born, switching on like a brilliant lantern in the dark. For most of its life, the star exists in a delicate balance, its inward crush of gravity perfectly countered by the outward pressure from the fusion furnace in its core. It is in this stable, prolonged phase that the star performs its most vital work, acting as a cosmic forge. It fuses the simplest element, hydrogen, into helium. In stars more massive than our Sun, this process continues, building ever heavier elements like carbon and oxygen in concentric shells within its heart. This is the universe's primary method of alchemy, transforming the primordial hydrogen from the Big Bang into the diverse elements of the periodic table. The star becomes a factory, silently manufacturing the very ingredients for complexity. But this creation cannot stay locked away forever. The star's eventual death is what scatters these treasures across the galaxy. For a massive star, death is a spectacular and violent release. Once it begins fusing iron in its core, the fusion process no longer produces outward pressure. The star's balancing act fails catastrophically. Its core collapses in upon itself in less than a second, then rebounds in a titanic shockwave that blasts the star's outer layers into space at incredible speeds. This is a supernova explosion, an event so brilliant it can outshine an entire galaxy. In this fleeting, ferocious inferno, conditions become so extreme that every element heavier than iron is forged, from the gold in a wedding ring to the uranium in the Earth's crust. The supernova then hurls this newly created, enriched material far and wide, seeding the surrounding interstellar medium with a fresh supply of heavy elements. This stardust, this ash from a stellar funeral, mingles with the primordial gas of the galaxy. Over millions of years, gravity will pull this enriched material together once more, forming a new generation of stars. But this time, the story is different. The swirling cloud of gas and dust that collapses will now contain not just hydrogen and helium, but also carbon, oxygen, nitrogen, and iron. These elements allow the gas to cool more efficiently, enabling the formation of rocky planets around the new star. This continuous cycle of stellar birth, death, and rebirth is a fundamental sculpting process. It does not build vast structures like the cosmic web, but it populates them with the chemistry for planets and life. This means the universe is fundamentally interconnected through a grand recycling program. The oxygen we breathe, the calcium in our bones, the iron in our blood, every atom in our bodies beyond the simplest hydrogen was once manufactured in the heart of a long-dead star and then scattered by its explosive death. We are not just living in the universe, we are literally made from it, products of this relentless cosmic cycle. The distribution of these heavy elements is not even. The centers of galaxies, where stars have lived and died in rapid succession for billions of years, are far more metal-rich than the sparse outer suburbs. This chemical enrichment, governed by the fundamental nuclear forces inside stars, paints a detailed history onto the large-scale structures carved by gravity and dark matter. It dictates where Earth-like planets are most likely to form and where the chemistry for life is most abundant. The forces that bind atomic nuclei together are just as much cosmic sculptors as the force of gravity, working on an intimate, elemental scale to create the conditions for complexity. This cycle raises a profound question about our own place in the cosmos, connecting the fate of distant, long-vanished suns to our very existence. While gravity provides the grand architecture, the universe's fine details are etched by a different hand. Electromagnetism is the artist of the intimate, the force behind every flicker of starlight and the intricate traceries that adorn the cosmos. It governs the behavior of charged particles, and in a universe where most visible matter is superheated into a fourth state called plasma, this force is king. Plasma is simply a gas so energetic that its atoms have been torn apart, creating a seething soup of free electrons and atomic nuclei, all responding instantly to electromagnetic commands. This is the force that makes a star shine, its relentless fusion reactions generating light itself, an electromagnetic wave traveling across the void to reach our eyes. But its artistry extends far beyond mere illumination. Within a star's atmosphere, electromagnetism weaves complex magnetic field lines, colossal loops of invisible force that can trap and channel glowing plasma, sculpting it into magnificent arches known as solar prominences, which dwarf entire planets. These magnetic interactions are not confined to stars. They shape the glowing tails of comets, pushing them away from the sun. They drive the spectacular auroras that dance in planetary skies as charged particles from the solar wind spiral along a world's magnetic field lines. This force adds the vibrant color, the dynamic light, and the delicate texture to the cosmic sculpture, working on a human scale we can directly observe and appreciate. And one of its most breathtaking masterpieces is the nebula. These vast clouds of gas and dust are electromagnetism's canvas. Within them, the light from nearby stars, especially energetic young ones, energizes the gas, causing it to glow in ethereal hues of red, blue, and green. Intricate magnetic fields can then sculpt this glowing plasma into fantastic shapes, pillars, and bubbles, creating celestial landscapes of unimaginable beauty. The famous pillars of creation within the Eagle Nebula are a perfect example, where dark, dense columns of dust are simultaneously eroded and illuminated by the fierce stellar winds and radiation from newborn stars. Here, electromagnetism is not just a painter of light, but a literal sculptor, carving delicate structures that persist for mere cosmic moments, a fleeting, exquisite detail in the endless work of art. These glowing clouds are the universe's most vibrant workshops. A nebula is far more than a beautiful cosmic painting. It is a dynamic factory of creation and destruction, a place where the raw materials of existence are forged into new forms. The most famous of these, the Great Orion Nebula, is a stellar nursery. Here, vast clouds of cold hydrogen gas collapse under their own weight, fragmenting into dense knots that will one day ignite as new suns. The most massive of these newborn stars are searingly hot, and they flood the surrounding gas with intense ultraviolet radiation. This powerful light strips electrons from the atoms in the gas, causing the entire cloud to ionize and glow with a characteristic red hue. This is an emission nebula, a birthplace illuminated from within. Other clouds, known as reflection nebulae, lack these internal powerhouses. They are simply vast fields of dust that act like cosmic fog, scattering and reflecting the blue light from nearby stars, giving them a soft, ethereal glow. But not all nebulae signal a beginning. Some mark a spectacular end. When a star like our Sun dies, it does not explode. Instead, it gently puffs its outer layers into space over thousands of years. The exposed, hot core of the star then bathes this expanding shell of gas in ultraviolet light, causing it to fluoresce in brilliant, intricate patterns. These are planetary nebulae, though they have nothing to do with planets. Their often symmetrical shapes, from perfect rings to delicate butterfly wings, are sculpted by complex interactions between the dying star's winds and magnetic fields. On a far more violent scale, a supernova remnant is the chaotic wreckage from the explosion of a massive star. The blast wave slams into the surrounding interstellar medium at millions of kilometers per hour, compressing and heating the gas and forging heavy elements in the process. These remnants often appear as ragged, expanding shells of glowing filaments, the scattered ashes of a stellar giant. Within all these clouds, the forces of radiation and magnetism are constantly at work. The fierce stellar winds from young stars and the pressure of their light can push material away, carving out vast cavities and leaving behind dense, towering pillars like the pillars of creation. These pillars are not monuments of stone, but transient sculptures of gas and dust, their forms constantly being eroded by the very forces that revealed them. And deep within the darkest, coldest cores of these nebulae, another profound process begins. As a new star switches on at the center of a collapsing cloud, the leftover material forms a spinning, flattened disk around it. Within this protoplanetary disk, microscopic particles of dust begin to stick together, growing into pebbles, then rocks, and eventually, over millions of years, into full-fledged planets. Every world in every solar system, including our own Earth, was assembled within such a dusty disk surrounding an infant star. These nebulous clouds are the cosmic crossroads where the grand cycle of matter is made visible, where the death of one generation of stars directly provides the substance for the birth of the next. Within that swirling disk of dust and gas surrounding a newborn star, a new, intimate act of cosmic sculpting unfolds. This protoplanetary disk is a chaotic, miniature workshop, a spinning storm of potential where planets are painstakingly assembled, piece by microscopic piece. The process begins with the finest of materials, mere specks of dust and ice left over from the star's formation. Within the disk's dense, dark regions, these tiny particles drift and gently collide. Instead of shattering, static electricity and molecular forces make them stick together like cosmic dust bunnies. Over thousands of years, these microscopic grains grow into pebbles. The pebbles gather into boulders, and the boulders, through countless gentle mergers, become mountain-sized bodies called planetesimals. This is the foundational stage, building the planetary bricks from which worlds will be made. Gravity then takes a more direct hand. The largest of these planetesimals exert a stronger gravitational pull, drawing in more material and clearing a path along their orbit. They grow into protoplanets, the infant cores of future worlds. In the hot inner regions of the disk, close to the brilliant young star, only metals and silicate rocks can remain solid. Here, the growing bodies become the seeds of rocky, terrestrial planets like Earth and Mars. Farther out beyond the frost line, where temperatures are cold enough for volatile ices to exist, the protoplanetary cores grow much larger. They become massive enough to grab hold of the vast envelopes of hydrogen and helium gas that still swirl in the disk, rapidly swelling into the gas giants like Jupiter and Saturn. This gravitational sorting creates the distinct architecture of a solar system, a clear division between the compact inner worlds and the majestic outer giants. But this construction phase is far from peaceful. It is a time of immense violence and chaos. Young protoplanets jostle for position, their orbits crossing and interacting. Cataclysmic collisions are commonplace, with some mergers building larger worlds and others shattering bodies back into debris. The immense gravity of the growing gas giants can act like a gravitational wrecking ball, scattering smaller planets inward or flinging them out into the dark void of interstellar space, forever doomed to wander as rogue planets. The entire system is a dynamic, shifting puzzle. Finally, the young star itself puts the finishing touches on its planetary family. As the star ignites its fusion engine in earnest, it begins to blast out a powerful solar wind and intense radiation. This stellar fury acts like a cosmic blowtorch, sweeping through the system and pushing the leftover hydrogen and helium gas out into interstellar space. This process strips the inner planets of their primitive gaseous atmospheres, leaving behind the bare, rocky worlds we recognize today. It halts the growth of the gas giants by cutting off their fuel supply, finalizing the basic structure of the entire system. Our own solar system, with its 8 planets orbiting in a relatively flat plane, is a perfect example of this completed sculpture. Its current, seemingly stable arrangement is a frozen record of that violent, dynamic past, a snapshot of the chaos that once reigned. And for each of these newly formed worlds, a new chapter of sculpting is just beginning. The face of our moon is a permanent record of cosmic violence, a landscape frozen in time. Its countless craters are the scars from a chaotic era known as the Late Heavy Bombardment, a period when the inner solar system was a shooting gallery of leftover planetesimals and debris. Each impact was a cataclysm, releasing more energy than all our nuclear arsenals combined, blasting out vast basins and spraying ejected material across the lunar surface. This relentless pounding did more than just leave marks. It churned the entire outer layer of the moon into a broken, powdery regolith, and it delivered vast quantities of water ice and volatile compounds to permanently shadowed polar craters. This process of impact cratering was a fundamental sculptor for every solid body in our early solar system, from Mercury's scorched plains to the frozen, icy surfaces of moons orbiting the gas giants. It was the universe's way of delivering the final building blocks and hammering worlds into their initial forms. Yet some worlds refused to remain static museums of impact. On a geologically active planet like our Earth, a far more dynamic and continuous set of sculpting forces took over. The primary driver is the planet's internal heat, a remnant from its violent formation and the slow radioactive decay of elements deep within its core. This heat keeps the planet's interior plastic, fueling the immense engine of plate tectonics. The planet's brittle outer shell is broken into massive plates that slowly drift, jostle, and collide on a timescale of millions of years. Where these plates crumple together, they thrust up colossal mountain ranges like the Himalayas, pushing rock that was once at the bottom of an ocean to the top of the world. Where they pull apart, they create vast rifts, allowing molten rock from the mantle to well up and form new crust, a process that continually reshapes the ocean floors. This slow-motion dance of continents is the primary architect of our planet's grandest landscapes. Volcanism acts as another powerful chisel, a direct pipeline from the planet's fiery interior to its surface. It builds entire mountain chains like the Cascades, creates new islands in the middle of the ocean, and floods vast regions with thick layers of basalt, forming great plains. But the most patient and detailed sculptors are the forces of erosion powered by the sun. A planet with an atmosphere and liquid water becomes a canvas for weather. Wind slowly sandblasts rock into strange, fluid shapes. Rain dissolves minerals and carves intricate networks of streams and rivers. Over millennia, a single river can slice through a mile of solid rock, creating a canyon of breathtaking scale. Glaciers, immense rivers of ice, grind entire valleys into U-shaped troughs and deposit the rubble as moraines. Even the constant pulse of waves against a shoreline is a form of sculpting, constantly redrawing the boundary between land and sea to create beaches, cliffs, and arches. These processes work in concert, with tectonic forces building the land up and erosive forces tirelessly wearing it down. This grand geological story is written uniquely on every body we observe. Mars bears the unmistakable signs of a complex past, with the solar system's largest volcano, Olympus Mons, and a canyon system, Valles Marineris, so vast it would stretch across the entire United States. These features hint at a world that once had a more active interior and perhaps even flowing water on its surface. Venus, shrouded in a thick, acidic atmosphere, shows evidence of rampant volcanism, and a surface that may have been completely resurfaced by lava flows in a relatively recent cataclysm. Even small, icy moons like Jupiter's Europa are being sculpted, not by internal rock, but by the tidal flexing from their giant planet, which heats their interiors enough to maintain a global ocean beneath a fractured, icy crust. The geology of a world is its biography, a record of its internal vitality, its atmospheric history, and its place in the solar system. From the grandest mountain to the smallest sand grain, every detail tells a chapter in the epic of cosmic sculpting. The final chips and shavings from the cosmic workshop still drift through our solar system. Asteroids and comets are these leftover fragments, the raw materials that never made it into a planet or moon. The asteroid belt, that vast ring of rubble between the orbits of Mars and Jupiter, is a celestial junkyard. These are not the closely packed, tumbling rocks of science fiction, but millions of worlds separated by immense distances, each one a silent relic. Their shapes are rarely spherical, but instead look like cosmic potatoes, battered and pitted from billions of years of mutual collisions. They are the rocky remnants of the solar system's construction site, pieces of a planet that never was, held in check by the immense gravity of nearby Jupiter. Far beyond the realm of the planets, in the deep freeze of the outer solar system, reside the comets. These are not rocky but icy. They originate in two vast reservoirs, the Kuiper belt just beyond Neptune, and the distant, spherical Oort cloud at the very edge of the Sun's gravitational influence. These icy bodies are pristine time capsules, preserving the original, frozen ingredients of the solar system's birth. When a comet's long, elliptical orbit brings it plunging inward toward the Sun, it undergoes a spectacular transformation. The Sun's heat warms its surface, causing the frozen ices within to turn directly into gas, a process called sublimation. This erupting gas drags dust with it, creating the comet's magnificent, glowing head and its iconic twin tails. One tail, a stream of ionized gas, glows blue and is blown directly away from the Sun by the solar wind. The other, a broader, curving dust tail, reflects sunlight with a soft, golden glow. These tails always point away from the Sun, a celestial windsock showing the direction of the solar breeze. To consider these small bodies insignificant is to miss their profound role in the story of life. The early Earth was a scorching, molten world. Its original water likely boiled away. Scientists believe that much of the water in our oceans and the complex organic molecules that are the building blocks of life were delivered later by a relentless rain of comets and water-rich asteroids. These cosmic messengers brought the essential ingredients for our world's oceans and potentially for life itself. Their impacts are not just a thing of the distant past. The cratered face of the Moon is a permanent reminder of a violent era, and events like the 1908 Tunguska impact in Siberia, which flattened 2,000 square kilometers of forest, show that this sculpting process continues. The journey of every asteroid and comet is a beautiful demonstration of orbital mechanics, a delicate and predictable dance governed by gravity, a reminder that even the smallest chips from the sculptor's workshop follow the universe's immutable laws. These gravitational dances are not chaotic, but rhythmic and mathematical. Orbital resonance is a subtle form of cosmic choreography, a repeating pattern where two or more orbiting bodies exert a gentle, regular tug on one another. For every certain number of orbits one body completes, the other completes a precise number, locking their motions into a stable, repeating cycle. This is the hidden music of the solar system, a harmony written in the language of gravity. A beautiful and intimate example is the dance between Pluto and its largest moon, Charon. They are locked in a perfect one-to-one resonance, always showing the same face to each other as they whirl through the void. It is as if they are forever in a cosmic embrace, perpetually connected. A more complex symphony plays out among three of Jupiter's largest moons. Io, Europa, and Ganymede are locked in what is known as a Laplace resonance. For every single orbit Ganymede makes around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise, repeating alignment means these moons regularly tug each other into slightly elliptical, non-circular orbits. This constant gravitational kneading from Jupiter and its other moons generates immense internal friction and heat through tidal forces. The result is spectacularly violent on the closest moon, Io. This relentless heating makes Io the most volcanically active world we know, its surface a constantly changing canvas of erupting plumes and flowing lava. Meanwhile, the same resonant forces are believed to keep a global ocean of liquid water sloshing beneath the icy crust of Europa. Here, orbital resonance is not just a geometric curiosity, it is the engine for geological activity and a potential haven for life. But this celestial music can also clear a room. Within the asteroid belt between Mars and Jupiter, there are stark, empty bands known as the Kirkwood Gaps. These are regions where any asteroid would fall into an orbital resonance with Jupiter. An asteroid in one of these gaps, for example, might orbit the Sun 3 times for every one of Jupiter's orbits. This repeated, periodic tug from the giant planet acts like a steady push on a child's swing, gradually adding energy until the asteroid is flung into a completely new, often unstable path. In this way, resonance acts as a powerful vacuum, sweeping certain orbits clean and sculpting the overall structure of the belt. These stable and unstable patterns are a direct and beautiful consequence of gravity's universal laws. They show us that the solar system is not a random collection of objects, but an intricate machine whose moving parts are finely tuned by an invisible, mathematical hand. This gravitational harmony dictates which orbits can persist for billions of years and which are doomed to chaos, ultimately determining the long-term architecture of entire planetary systems. These fundamental rules are written into the fabric of reality itself. The Cosmic Sculptors do not work with limitless freedom. They operate within a strict and precise rulebook defined by the universe's fundamental constants. These are not numbers we invented. They are intrinsic properties of reality, fixed values that dictate how everything behaves. The speed of light in a vacuum is always exactly 299,792,458 meters per second. The strength of the gravitational force is set by a specific, unchanging number. Even the mass of an electron and the charge it carries are precisely defined. This cosmic rulebook is what makes the universe predictable and orderly, allowing for the same laws of physics to apply from our laboratory on Earth to the most distant quasar. It is this consistency that allows gravity to build galaxies and nuclear forces to forge stars. But the most astonishing thing is not that these rules exist, but that their specific values are perfectly calibrated for creation. The strength of gravity is a prime example. If the gravitational constant were just a tiny bit stronger, the universe's expansion after the Big Bang would have been quickly overcome. All matter would have been pulled back together in a catastrophic reversal, a big crunch before stars or galaxies could ever form. The entire cosmic story would have ended almost as soon as it began. Conversely, if gravity were even slightly weaker, its pull would have been too feeble to gather the primordial gas. Those delicate density ripples in the early universe would never have grown. No stars would have ignited, no galaxies would have spun, and the cosmos would have remained a forever expanding, dark and formless haze. The same perfect balance is found in the nuclear forces. The force that binds atomic nuclei together has to be exquisitely tuned. If the strong nuclear force were a little more powerful, all the hydrogen in the early universe would have fused into helium almost instantly, leaving no fuel for the long-lived stars like our Sun that are necessary for life. If it were weaker, protons could never stick together and no complex elements would ever be forged. There would be no carbon, no oxygen, and no chemistry beyond the simplest atoms. This apparent fine-tuning extends to dozens of these fundamental numbers. It is as if the universe's dials were set with incredible precision to allow for a cosmos that is not only structured but also habitable. Why does the rulebook read this way? This is one of the most profound questions in all of science. Is this meticulous calibration simply a staggering, one in a gazillion cosmic coincidence? Or does it point to a deeper, underlying principle we have yet to discover? One compelling, though speculative, answer lies in the concept of a multiverse. This idea suggests that our universe, with its particular set of rules, might be just one bubble in a vast, possibly infinite, cosmic foam. In other universes, the constants could be radically different. In most of those other bubbles, the rules would be wrong for complexity, resulting in empty, short-lived, or chaotic realities. We find ourselves in this one, not because it is special, but because it is one of the rare versions where the constants allowed for galaxies, planets, and observers to arise. The fundamental constants are the ultimate sculptor's tools, and their precise, mysterious settings have carved a universe capable of wondering about its own existence. This grand cosmic rulebook, with its perfectly tuned constants, leads to a staggering possibility. What if our entire universe, with all its galaxies and laws, is just one page in an infinite library? This is the Multiverse Hypothesis, a vision of reality so vast it defies easy comprehension. In this picture, our Big Bang was not a unique beginning, but a single bubble inflating within a much greater, perhaps eternal, metaverse. Each of these cosmic bubbles could be a separate universe, each with its own random selection of physical constants and fundamental forces. In the overwhelming majority of these universes, the numbers would be wrong. Gravity might be too weak to form any structures at all, or the nuclear forces might be too strong, causing all matter to collapse instantly into black holes. These would be stillborn worlds, empty voids, or chaotic realms where nothing enduring could ever take shape. But in an exceptionally rare few, by pure statistical chance, the dials would be set just right. In those select universes, the Cosmic Sculptors would find the tools they need. Gravity would be strong enough to pull galaxies together, but not so strong as to cause a swift collapse. Nuclear forces would be balanced to allow for long-lived stars and the forging of complex elements. In this view, our universe is not special, it is simply lucky. We find ourselves in one of the few cosmic neighborhoods where the rules allowed for sculptors like gravity and electromagnetism to get to work, ultimately leading to planets, life, and curious minds that can look up and wonder. The profound fine-tuning we observe would not require a fine-tuner, only an immense landscape of possibilities where even the most unlikely outcomes must occur somewhere. While this idea is currently beyond the reach of direct experimental proof, it represents a frontier of theoretical physics, a potential explanation that replaces the question of why our constants are perfect with the answer that every possible set of constants exists somewhere. It transforms our universe from a single, inevitable masterpiece into one unique sculpture in an endless gallery of realities, most of which are formless and dark. This brings our journey from the theoretical to the tangible, back to the question of how we, from our tiny vantage point, can possibly observe these grand designs. Humanity's journey to perceive these cosmic sculptures has been a story of building better eyes. It began with a simple spyglass when Galileo first turned his instrument toward the heavens and saw the craters on our moon and the moons orbiting Jupiter. That single act peeled back the first layer of the cosmic onion, revealing a universe far more detailed and dynamic than anyone had dreamed. Each technological leap since has removed another veil. Ground-based observatories perched on mountain peaks above the thickest air now use a brilliant trick called adaptive optics. They fire a laser into the upper atmosphere to create an artificial guide star, and then a computer deforms the telescope's mirror thousands of times per second to cancel out the shimmering distortion of our air. The result is a view from the ground that can rival the clarity of space, but to see the universe in its full, unobstructed glory, we had to leave our atmosphere behind. The Hubble Space Telescope became our first permanent window on the cosmos, its crystal-clear vision revealing the birth of stars, the death of galaxies, and the accelerating expansion of the universe itself. Now, the James Webb Space Telescope peers even deeper. Its infrared eyes, sensitive to the heat, glow from the first stars and galaxies, seeing back to an era when the cosmic sculptures were just beginning to take form. Yet our cosmic vision extends far beyond the light our eyes can see. We listen to the universe as well. Vast arrays of radio telescopes, like the Very Large Array with its 27 dish antennas spread across a desert plain, map the distribution of cold, neutral hydrogen gas, the primary fuel for star formation. They trace the invisible structure of galaxies. In the high-energy realm, space observatories like Chandra detect X-rays, allowing us to study the superheated plasma that fills galaxy clusters and the violent environments around black holes. And in one of the most profound breakthroughs, we have learned to feel the universe. Instruments like LIGO do not see light at all, they listen. They detect the incredibly faint ripples in spacetime itself, vibrations caused by the most cataclysmic events, like the merger of two black holes over 1 billion light-years away. Each of these tools provides a different sense for a universe that operates across a full spectrum of energy and phenomenon. Together, they are our windows into the sculptor's studio, allowing us to gather the clues and reverse engineer the grand processes that shaped everything we see. The data they collect is not just a picture, it is a river of information, a complex digital record of the cosmos that requires another kind of tool entirely to decipher. These rivers of astronomical data pour into the world's most powerful supercomputers, which translate them into entire digital universes. Cosmological simulations are our ultimate testing ground, a virtual laboratory where we can watch the cosmic sculptors at work from the first second to the present day. The process begins by programming the known laws of physics and the initial conditions from the Big Bang, including that faint, frozen imprint of sound waves from the cosmic microwave background. Then, with a press of a button, the simulation begins. It models the gravitational pull of dark matter, the hydrodynamics of swirling gas, the ignition of stars, and the explosive feedback from supernova and black holes. Projects like Illustris TNG and Eagle use billions of simulated particles to represent dark matter and gas, tracing their evolution over more than 13 billion years of cosmic history. Running one of these simulations can require months of continuous calculation on thousands of computer processors working in tandem, all to rewind and then fast-forward the entire story of our universe. The final result is not just a static image, but a dynamic, evolving map. You can watch as the invisible scaffolding of dark matter first condenses into a delicate cosmic web. You can see where the filaments intersect and witness the birth of a galaxy cluster, watching as gas flows along the dark matter highways, cools, and collapses into the first stars. These virtual galaxies even develop their own spiral arms, central bulges, and satellite companions, mirroring the diversity we see through our telescopes. The true power of these simulations lies in the ability to compare. Astronomers can take a snapshot of their digital universe and place it side by side with deep field images from Hubble or James Webb. Does the simulation produce the right number of elliptical versus spiral galaxies? Do the virtual galaxies have the correct sizes, luminosities, and chemical compositions? When the digital cosmos closely matches the real one, it gives us tremendous confidence that our understanding of the underlying physics, from the role of dark matter to the impact of black hole feedback, is on the right track. If there is a mismatch, it reveals a gap in our knowledge, pointing toward a physical process we may have overlooked or misunderstood. We can even run experiments that are impossible in reality. What would galaxies look like if dark matter interacted with itself? What if we turned off the explosive power of supernova? By tweaking these cosmic recipes, we learn which ingredients are essential for sculpting a universe that looks like our own. These digital universes are more than just movies. They are a crucial bridge, allowing us to witness the invisible forces that carved our home out of the void. Even with our most powerful digital recreations, the blueprint of the cosmos remains profoundly incomplete. We have mapped the grand design, but the fundamental nature of the architects themselves is still a mystery. The true identity of dark matter is perhaps the greatest of these puzzles. Is it a sea of undiscovered particles, 1 trillion times more massive than a proton, streaming through our bodies at every moment without a trace? Or could it be that our understanding of gravity itself is subtly wrong on the vast scales of galaxies, requiring a tweak to Einstein's equations rather than an invisible substance? We simply do not know. Compounding this mystery is the enigma of dark energy. Is it a constant energy woven into the very vacuum of space, or a dynamic field that has changed over the lifetime of the universe? The answers will dictate the final fate of everything. If dark energy remains constant, the cosmos will expand forever, growing ever colder and darker in a gradual big freeze. If it strengthens over time, it could ultimately tear apart galaxies, stars, and even the fabric of spacetime itself in a catastrophic big rip. These are not abstract ideas, they are competing visions for the ultimate end of reality. Another stubborn question lies at the heart of nearly every galaxy. How did the supermassive black holes residing there grow so immense so quickly? Observations of the most distant quasars, blazing from when the universe was less than 1 billion years old, show black holes already weighing billions of solar masses. There seems to have been hardly enough time for them to grow so large by slowly feeding on gas. Did they form from the direct collapse of enormous primordial gas clouds, bypassing the star stage entirely? Or were the seeds for these monsters planted in the very first moments of the Big Bang? The sheer speed of their formation challenges our models of cosmic evolution. The most humbling fact in all of cosmology is that the stuff we understand, the ordinary atoms that make up every star, planet, and person, accounts for a mere 5% of the universe's total content. The remaining 95% is this unknown territory of dark matter and dark energy. This is not a small gap in our knowledge, it is a chasm. We are like cartographers who have beautifully mapped the coastlines of a continent, but have yet to explore the vast, dark interior that defines its true mass and nature. These unanswered questions are not a sign of failure, but the very definition of the frontier. They are the limits of our current chisel, the point where our tools of observation and theory meet the hard stone of the unknown. The pursuit of these answers is what drives the construction of ever more sensitive detectors deep underground, searching for a whisper of dark matter. It motivates the planning of immense new telescopes, both on the ground and in space, designed to measure the effects of dark energy with unprecedented precision. This relentless curiosity is how we sharpen our tools, ready to carve deeper into the mysteries of cosmic design. We are not separate from the cosmic art we observe. We are a part of its very fabric. Every element in our bodies that is heavier than hydrogen tells a story of stellar alchemy. The calcium in your bones was forged in the final moments of a massive star's life, during the intense heat of a supernova explosion. The oxygen you just breathed into your lungs was created through the steady, patient fusion inside a sun-like star that shone billions of years ago. That star lived its long life and then gently returned its enriched contents to the galactic reservoir, where it eventually became part of the cloud that gave birth to our solar system, our planet, and us. We are not just living in the universe, we are literally remnants of its most violent and creative processes. The iron that carries oxygen through your bloodstream is a direct product of stellar death, a relic from a cosmic event that occurred long before the Earth even formed. This physical connection is undeniable, written into the chemistry of our own bodies, but the connection runs even deeper than shared ingredients. The same fundamental forces that orchestrate the grandest designs also govern the smallest realms. The gravitational constant that guides the majestic dance of galaxies is the very same force that anchors your feet to the ground. The electromagnetic force that binds atoms together into molecules here on Earth is identical to the force that makes a distant star shine. There is no separate set of rules for the cosmos and for us. We are subject to the same cosmic rulebook, playing out the same physical laws on a human scale. This shared reality means that by studying the world around us, from the fall of an apple to the spectrum of a distant nebula, we are deciphering the universal language of the sculptors. Our curiosity, our drive to build telescopes and particle accelerators, is not an isolated human whim. It is the universe's own capacity for reflection awakening within one of its creations. In a very real sense, the cosmos has begun to look back at itself through our eyes, to measure its own expanse and to ponder its own origins. we are a fleeting but conscious expression of the universe's ongoing creativity. This perspective does not make us small or insignificant. It weaves our personal story, with all its individual hopes and struggles, directly into the grandest narrative there is. Your very existence is a temporary gathering of ancient stardust, granted a brief moment of awareness to contemplate the magnificent sculpture from which it came. Our current view of the cosmos is about to be transformed. The next decade will launch a new era of discovery, equipping us with tools of unprecedented power to finally see the work of the cosmic sculptors in crisp, undeniable detail. The Vera C. Rubin Observatory, perched atop a mountain in Chile, will soon begin a monumental 10-year survey of the entire southern sky. Its massive mirror and enormous digital camera will capture the heavens in such detail that it will catalogue billions of galaxies, watching how their light is stretched by the expanding universe over time. This vast time-lapse map of cosmic structure could be the key that unlocks the stubborn mystery of dark energy, revealing whether its repulsive force has changed over the lifetime of the cosmos. While Rubin scans the sky with light, another mission will listen to the universe in an entirely new way. The LISA mission, a fleet of 3 spacecraft flying in a perfect triangle millions of kilometers apart, will detect the low-frequency ripples in spacetime generated by the mergers of supermassive black holes. This will allow us to hear the echoes of events that are completely invisible to traditional telescopes, probing the gravitational dynamics at the very hearts of galaxies. Meanwhile, here on the ground, a new generation of colossal telescopes is taking shape. These 30-meter-class giants will gather so much light that they can analyze the faint atmospheres of planets orbiting other stars, searching for the chemical signatures of water, oxygen, and methane. The sheer volume of data from these new eyes will be unimaginable, a deluge of cosmic information. To make sense of it all, we will rely on advanced artificial intelligence to sift through the noise, identifying subtle patterns and anomalies that would escape any human eye. These intelligent systems will help us trace the faintest filaments of the cosmic web, map the distribution of dark matter with finer precision than ever before, and perhaps even flag the existence of phenomena we have not yet dreamed of. We are not merely building better telescopes, we are constructing an entirely new sensory apparatus for humanity. The golden age of cosmology is not behind us, it is just beginning. Our understanding of the grand cosmic design, still fragmented and filled with questions, is poised for a monumental leap into the unknown. Our journey reveals a cosmos in perpetual motion, shaped by a dialogue between forces seen and unseen. From the subtle warping of spacetime to the invisible scaffold of dark matter, and from the explosive feedback of black holes to the relentless push of dark energy, we have traced the work of the cosmic sculptors. This is not a static museum piece, but a living, breathing masterpiece, its grandest designs emerging from the interplay of construction and dispersal, of chaos and order. We now understand that the universe is profoundly interconnected, governed by a precise and beautiful set of physical laws that allow for galaxies, stars, planets, and life itself to arise. This exploration leaves us with a humbling and awe-inspiring vision, a cosmos far more wondrous and complex than we ever could have dreamed. Every time your eyes meet the night sky, you are witnessing this ongoing work, a creation billions of years in the making that continues to unfold. If this journey through the cosmos has expanded your mind, consider subscribing for more deep dives into the universe's greatest mysteries, and share your thoughts on these cosmic sculptors in the comments below.